talk today, we're not going to dive into a ton of code necessarily, but I want to tell you about the work that we've been working on for the last 7 years. It is an application entirely written in Scala, and we're open sourcing it today, and would love to have folks come to the GitHub page and take a look and contribute anything to the code or make use of it in whatever way looks interesting and seems interesting to you. But for today's talk, we're going to give a quick overview about what is Quine. So first, what is it? How does it work? And given how it works, what kind of new capabilities do we get as a result? And then I'll pause for a demo. I'll show you it running and operating, and we'll close with a discussion real quick of where it fits in and a little bit about what we've learned over the process of developing it here. So let's start. What is Quine? First, a real quick disambiguation here. Quine is several things, as we were hinting at a little bit. For us, Quine is a streaming graph. So it's meant for modern data pipelines to consume data, put it into a graph, analyze that real fast on the fly, and continue. But the name is already in use in a couple different places here. You might know the term from computer science where a quine is a program that outputs its own source code. So that term has been around since Douglas Hofstadter and Gödel Escher Bach, I think it was. But both of these things are actually harken back to the 20th century philosopher Willard Van Orman Quine. He did a lot of work in philosophy of language and logic. A lot of what computer systems depend on comes down to the logical formulae and logical innovations that he had pioneered. Quine is also the originator of terms like functor and referential transparency. And so in some ways, I kind of think of him as like a godfather of functional programming in this way. If I had to distill functional programming down to its essence, referential transparency, I think would be very high on the list. So Quine means several different things. We just wanted to start by acknowledging that. But for us, it means a streaming graph. So let's talk about the streaming problem, the situation in the world right now, what it looks like to build streaming data pipelines. This tends to be a very Scala-oriented problem. Lots of Scala applications are around data pipelines and high-volume systems that move data through and interpret them. Or even the data science around doing that interpretation. The pipeline itself is really the topic of conversation for us today, and talking about the interpretation step. And yeah, Scala engineers are probably very familiar with this sort of thing. It's very easy, right? So you collect the requirements for your stream, you get going, and it's all done, right? Except that we have to support really high volumes of data, really low latency requirements. You have to fit a lot of things in RAM to make it fast enough along the way. That RAM tends to be the most expensive part of the infrastructure you run on. You typically have to settle for time windows that you're going to set and configure based on how much RAM you have for joining together data from multiple different sources. If an A arrives before a B, you have to hold on to the A long enough until the B arrives that you can join them together. But if they arrive too far apart, then maybe you run out of memory and you have to expire that A out of your cache. So a B arrives and gets joined to nothing, and you've missed the opportunity to correctly interpret that data. And so these systems tend to get built and spread across microservices architectures that require developers to then turn the database inside out. Which means understanding lots of details around how a database works, and then implementing it in a collection of microservices that can implement a lot of those features. It's hard to hire people who have that kind of background, and hard to find the expertise required to do that. But it can be a really fun exercise. Along the way, you'll have to confront your CAP theorem trade-offs and just typical technical trade-offs about what choices you make and what technology you use. Probably encountering questions about distributed transactions and order-dependent processing, where you have to do something first and you have later questions about, is another system guaranteed to have the data in time? And eventually, if something goes wrong, you need to debug something or produce an old report, then you set up a second data pipeline to ingest data and replay it up to the point that you want and get the answer that you need or do the debugging that you need to do. And so you can replay the data. But the net result is you can take data in and get to business value. The downside is you end up with something that kind of looks like this. But it is technically possible. So this works. This is my background, is building these kinds of systems. I've felt this pain for a long time and from a lot of different directions. And unfortunately, it typically has a lot of pain involved. It's hard to do, it takes a long time, and it's very error prone. Small, subtle little differences in expectations around microsystem component performances can have big impacts to the correctness of the final results. It's hard to find the team that is capable of building that and maintaining it. And because it's so complicated, if a couple people leave on the team, they take with them their tacit knowledge about subtle expectations of different components, and you may end up needing to rebuild the system because it's too hard to untangle some of the subtleties involved. So unfortunately, this tends to be the state of the art in the industry. And a lot of us kind of live this world and have to build our systems in this way. And this is really what we wanted to tackle and address when working on Quine. Quine is a streaming graph interpreter that is the result of more than 7 years of research and development, and is aimed at this problem of data pipelines, the complexity, the speed and throughput, and all the pieces that go into it. So if we look at Quine and from that perspective of how to interpret data in a streaming data pipeline, we get some different results. Quine's built from the ground up in a kind of a different sort of way, and different trade-offs as we go. It handles high volumes of data, low latency computation, that's great, low RAM requirements. So you can run it on a Raspberry Pi, you can run it on a big AWS server, and choose how much RAM you need or how much RAM is available on the environment you want to run it on. And it doesn't require huge amounts of RAM. There are no time windows, so you don't have to make that hard choice about joining data if it arrives within a minute or 10 minutes or however much RAM you have available for you. We've taken the perspective of saying, let's take Quine and kind of go through that process of turning the database inside out, but then also wrap it back up again so it's simple and easy to use. Let's approach the cap theorem trade-offs about how you'd run a system like this with a little bit of creativity, and maybe get to a convenient place where it's easy and convenient to run this in the presence of failure in high volume systems. Quine handles out of order data. So if data arrives from multiple streams outside of that time window, or even comes in backwards, Quine can assemble it all back together again and get the right answers streaming out. And we handle this order dependency with something we'll get to a little bit later that we call standing queries, that give us the ability to use data structure as the primary building block for what we're looking for. And so data transactions can essentially help us move past the philosophy of having to depend on the order of computation in order to get the right answer. And then lastly, it's great to have an answer for now, but also we want old data to become available and be able to be used in a streaming system without having to set up a whole new pipeline. And so in Quine, that past data is present and easily queryable. So you can query the past data that streamed by an hour ago, a minute ago, or a month ago. You can query that just as easily as you could query the present moment. So what is Quine? What is a streaming graph? In a nutshell, it's really these two sides of the coin: event-driven data and then data-driven events. On the event-driven data side, data streams in, and we use that to build an internal graph. And with that graph live and running and updating according to the data that's coming in, we set what we call standing queries on the data to watch that graph, watch it for certain patterns and shapes, and run complex queries on that graph. And that's what drives the events that come out of the system. So the data-driven events are the result of queries that are run live on that streaming graph in the system. What might we use it for? On the event-driven data side, it confronts many of the issues that we were talking about previously, high volume data coming in, so beyond just hundreds or thousands a second, but tens of thousands or hundreds of thousands, or even to millions of events per second. Combines streaming and batch data if need be. Join together lots of data streams, handle that out of order problem we were talking about. Remain flexible enough that you could add another data stream to this that doesn't have the structure that you were originally expecting when you set up your whole data pipeline. And to be able to run these historical queries on data as it comes through. The applications this is driving on the data-driven side we have users right now using this to build cutting-edge XDR platforms in the cybersecurity space. Our team has built some new graph AI techniques on top of this streaming graph. There are companies using it for CDN log monitoring, blockchain analysis, Kubernetes event monitoring, and we're kicking off some new projects right now for data cleansing pipelines for machine learning workflows. So lots of interesting things in a bunch of different domains happening. But if we look at that cybersecurity example for a second, the goal is to find an attack or find a data breach that might be happening. And a lot of cybersecurity companies are deployed in a way that they are collecting huge volumes of data just to understand what's happening. But our goal isn't actually to have all that data. That data is a means to an end. And so conceptually, our goal is actually to take data of many different kinds and start raising the level of abstraction through that interpretation process. Take the low-level data and start talking about what objects exist, like human-level objects. What events are happening with respect to those objects? If we're looking for a cybersecurity attack, what stages of an attack do those events represent? And finally, what we really care about is lose the data, but tell me about every attack that could be happening. There's a very timely obligatory XKCD just from yesterday about this data trap, that the goal is not really to have lots of data and even to analyze data. The goal is to reduce how much data we have so that high volume data might be coming in, but the output of our systems are high value data. So ideally, it's actually a small amount of high value data. It's exactly the right amount of high value data. That's the goal. So let's ask this question. How does such a thing work? This sounds kind of crazy. It sounds too good to be true, perhaps. I wouldn't blame anybody for holding that opinion. So let's go under the hood, and I'll describe some of the ideas and architecture behind what we've built. And the code is available on GitHub. So if you're curious and would like to dive in, by all means, please do. To start with, I've mentioned graph data several times now. Graph data is kind of special. It's a superset in a sense. Tables and trees, like from relational databases or JSON document stores, these are a subset of graph structured data. What you can represent in a graph can handle all the tables you could ever create, all the trees you could ever create. It's also true for lists and sets and singular values. So a graph is in a lot of ways the master abstraction over top of all these different data structures that we use in lots of different databases and data systems. But historically, graphs have been a bit slow and kind of for small toy projects. But if you haven't used previous graphs in the past, it looks basically like this. Data is represented with nodes. So each circle in this small little graph on the screen is a node, and it's connected to other data by edges. And each node in the graph can have any number of properties, so key value pairs on a node. And part of what makes a graph so expressive is that its data structure is so very similar to natural language. The subject predicate object structure of many human languages correlates directly to this node edge node pattern. So you can take a simple little graph like this and you can basically read it. That gives you a very expressive, flexible, and powerful way to model data. And what's unique about Quine is that we've taken that graph structured data and we've paired it with a graph structured computational model. So this is an async computational model. It's built on top of Akka and makes heavy use of the actor model, where every node in that graph essentially is an independent actor. So messages passed between actors is how communication happens throughout the graph. When a query is run, it is run and computing the results by passing messages under the hood. And this gives us kind of some superpowers behind the scenes because every node now becomes a little computational unit. And it can do arbitrary computation at any point in time. So to resolve a query or to process some incoming data, we could just direct that data to a single node and create its relevant structure, or we could initiate a more complex protocol that passes messages back and forth between several different nodes. We have a lot of power behind the scenes that is packed together with the data itself. And so how does that work for a single node under the hood? When data is stored from a single node, we do it in an event-sourced fashion. So Quine will take a node in the graph, it receives a message and says, update your values. If that instruction or if that incoming data actually has an effect, it actually causes the system to change or that particular node to change, then we compute and save just the change to disk. And we save it to an append-only log. And so that gives us, in a lot of ways, the best of both worlds. The in-memory version of a node backed by an actor can do arbitrary computation and can grow and change over time. But then it can also save its data very quickly in this write-ahead log style where it's writing minimal data to disk. That can be local on the same machine or can be done on can be saved off the machine that's running the graph on a different storage layer like Cassandra. But that event source pattern is what is essentially at the heart of the persistence layer for each node. That data persistence, as I mentioned, is swappable. So it can run from several different backends. We've got local and remote versions of this. So Cassandra tends to be what we use most often for production deployments. And RocksDB is a nice, fast, and ideal store for us on local single system. But the structure that we need from that is really just a key value store. And so we can fit to different kinds of data structures behind the scenes. And there's components inside the code called a persister that implement the interface into these different kinds of data stores under the hood. So you can choose the data store of preference or choose the right trade-offs for your particular workload, and Quine is configurable in that respect. So under the hood are probably some relatively familiar patterns. The actor model's been around since the 70s. But we start to make some crazier assumptions now, some different design choices that start to look a little funny. And it's because if we limit ourselves to just what is always done in the traditional ways to solve these problems, then we'd end up with all the same trade-offs as other systems. So to try to create something new, we said, let's get off the well-worn path. And let's go explore some new territory. And this is why it took our team for the last 7 years, the core R&D, to create Quine. We've had to cover a lot of the same territory, but we cover it with a new perspective. With a different starting point, we've been able to make different trade-offs along the way. And with different trade-offs, we get different capabilities those different capabilities can give us a new perspective on some of the classic problems in distributed systems and data storage systems. So we make a couple crazy assumptions. So since it's a stream processing system, we want it to be stateful so that we can forget about time windows, but we also have the expectation that it's infinite data. Data will never stop. Data will always keep coming. There's no end to it. So we have to plan for this infinite data. And to do that, we make another assumption that let's flip the equation around, and instead of creating data when it arrives, let's just start with the assumption that all nodes in the graph already exist, all of them. Everything that you could ever refer to in the graph exists already. It just doesn't have an interesting history to it yet. So we don't have to create nodes. We simply just start referring to them and doing things with them and set properties on them. So this essentially simplifies our CRUD model quite a bit so that it can be no create. We've just got updates to already existing nodes. A node itself is defined by its ID. So what makes a node unique is that it has its own particular ID. And that ID under the hood is really just a byte array. It can grow to be any size, but we've made what we call an ID provider to make working with that ID a bit more convenient and comfortable. So you can choose an ID provider that's just a long, or you can choose an ID provider that is UUIDs or even custom classes and can bake in special information. So customizable, and there are several built into the system already, as well as kind of the translation layer for making that easy and convenient to work with in terms of queries, even though it is a little more complex under the hood. And then the last thing I want to mention, we could probably talk about a lot of these things for a while, but the last thing I wanted to mention is that to refer to an infinite amount of data, an index is kind of a non-starter because you can't build an index for an infinite amount of data. So we've built some customizations into the query language that provide some special functions like ID from. So if you're going to refer to a node, you can use the data that you have at hand to produce an ID from that data. It's essentially a consistent hashing approach, but it gives us a way to quickly find and address specific nodes in a graph that may have already been referred to, may have an interesting history, or it may be the very first time. So let's ask this question now. What's this for? This approach, what does it give us? So I've been hinting at this all along, but first of all, graph queries. So we have data structured as a graph. It's a very powerful representation, and we can query it using Cypher. We wrote a custom compiler for Cypher that takes arbitrary Cypher queries from the OpenCypher project, compiles them down into an AST that we need internally to propagate throughout the actor network for doing that computation on the graph. And the takeaway there is that the end user's interface is really just queries. So you can query any particular pattern that you could express in Cypher. Cypher is a SQL-like language, a language similar to SQL. But as you can tell from that match statement on this example slide, there's a little bit of ASCII art built in to draw pictures that start looking like nodes and edges in between them. Cypher queries allow us to query the data as it currently is, as it's streaming through the system. But as we were mentioning, this event source strategy for saving data gives us the ability to also look at the history of changes to any particular node. And since we can look at the history of changes, and each node is backed by its own computational unit, that node can replay its history up to any point in time that we desire. So you can issue the same query that you issue for a current moment and just add a timestamp and say, tell me what this answer would have been a minute ago, or a second ago, or an hour, or a day, or a week, or a month. Any time period at all. And when we get whatever the correct answer was for that historical moment. So querying the past is some of the special capabilities that we get, and we can do this in the stream of data as it's coming through. But that's not all. I hinted at this earlier that Quine bakes in functionality that we call standing queries. It is a way to query the future of the data. A standing query is really just a cipher query. Actually, it's two, more on that in a little bit, but it's a cipher query set on the graph, and then it lives inside the graph. So one query remains resident. It's like a standing wave in the graph. Issue that query on the graph, and it will automatically propagate under the hood the compiled AST throughout the graph so that it can incrementally compute its match to the data that we're looking for. So as data changes under the hood, the actors are propagating portions of a query when it's relevant to the next node that gets connected. And in this way, the structure of the data becomes the ideal understanding of where to go next in the data to most efficiently find that match that is in the process of being created over time. So these are event-driven and lazily evaluated. And under the hood, we cache these partial results along the way. The net result is that you can look for a very complex pattern in the graph that'll be incrementally computed as data streams through at the ideal moment when it is cheapest to do so. And then when you finally do have the data structured so that it would produce a match, your complex pattern gets turned into a result immediately. And then you can define in your standing query what you want to do with that result. So do you want to log it to the console, publish it to another Kafka topic, make a call out to an external system, publish it to Slack? There's lots of options. You can even call back into the graph to make a different kind of update based on certain matches. And as soon as you start doing that, it gets very powerful and very interesting for what you can do here. And with standing queries and the stateful model under the hood, this is how we get to eliminating time windows. So set a standing query, stream data in, and that query gets matched with new data and old data, however old it happens to be. If it's stored in the stateful part of the system, then it's woken back up, added to the part of the query that's relevant, computed, results propagated, and results stream out. So let me show you what it looks like. I'm going to drop on my slides here for a second, and I've got a web browser here open at, so this is quine.io. You could go here right now and take a look if you'd like. We've got, hey, look, this is Scala Love. That's us right now. There's plenty of information on here, and we spent a while putting together documentation so that if you want to know, how do I get started with a system like this, you should be able to find the answer very quickly and easily right here. And any questions that come up along the way, here's a link to the Slack forum. And we've got folks from our team who'd love to help answer any questions. But let's go to download. I'm going to download the 1.0 release. It just came out today. I've got it downloading. And what I want to do with this is actually encapsulated pretty nicely in what we call recipe. So we're going to walk through this little example that we call Ethereum tag propagation. This is going to, with our newly downloaded jar here, I'm going to run it from the command line. And I'm going to show you a couple errors, actually, just real quick, just to point something out. Whoops. Jar. No being so loud here. I'm running this on an M1 Mac, and unfortunately, RocksDB is not compiled and released for it yet. So if you see right here, there's a message suggesting what to do in the meantime. There's a release coming for RocksDB to make this a little cleaner and easier and work a little better here, but I'm going to go ahead and pick up that, that option from the error here. And I'm gonna add in the option to say, -R, use a recipe, and use this, oops, spell it correctly, it's Ethereum recipe. Because I'm passing in special configuration to use MapDB instead of RocksDB, I'm also going to pass in this force config option to make sure that gets picked up. So just an example of starting and running a recipe. So there we go. Quine has started in the background. It is running. And let me tell you about this recipe and what it's meant to be doing. So this is actually connecting live to the Ethereum blockchain. So we have a server publishing an SSE endpoint, just for example purposes like this. It happens in bursts where there are new blocks mined. And when a new block is mined on the Ethereum blockchain, SSE events are published and picked up by Quine. All of that is defined here on the left in this recipe. So a recipe is a user-contributed workflow, essentially. So it's written in YAML. It describes what work to do behind the scenes, and then gets Quine started up and running and doing all of that. You don't have to use a recipe. You could start the server and use it directly through the REST API to control the system and stream events in through Kafka and Kinesis and others. But in this case, this recipe is defined in what you see on the left. It's going to pick up 2 ingest streams. Hopefully you can see that okay. 2 ingest streams, one of them coming from this URL and the other coming from this URL. There's a stream of blocks and a stream of mine transactions in here. So each of these streams has a cipher query set to build that incoming data into a graph structure. And then there's one standing query set down here. A standing query is going to watch that, that incoming structure for certain patterns, which I'll show you in a moment. But those patterns get matched in real time and trigger action. So let's go look at it here. This is running behind the scenes. We've got a couple convenience queries built in here. This is the blockchain as it has been streaming in while we've been talking. So I'm showing you the exploration UI, just as, clean up a couple things here, just as a way to visualize some of the data coming in. It's meant for small little subgraphs. You can see, if we mouse over this, it's probably very small, apologies. If we mouse over this, we can see what this data looks like. This is Ethereum data streaming in, and we can right click and go explore what's adjacent to it. We could type a query up here in the bar if we wanted to explore it a little bit more by hand. But I'm gonna start pinning some of these down so that we can explore it without them moving around. Double click this guy to get its adjacent nodes, and we see a bunch of transactions. So these are transactions that just happened. I don't know what's in them. It's just a live stream. Clean up a few of these. Let's investigate what's here. Also going to pin some of these down as we go. But here's a transaction from one account to another account. So this is the graph that it's building. It's not a high volume use case really, but Ethereum has relatively low traffic, but it's streaming in, building this graph behind the scenes. But as we hinted, it's also going to apply standing queries whenever they're relevant. And in this case, we set up this example so that it would show off a very, very powerful tool called tag propagation. In a graph, you can, well, we're going to set a tag on a node. In this case, we're going to follow the scenario that made the news a lot recently about finding crime by monitoring money laundering through a blockchain. And so if I suspected this account, apologies to whoever's account it is, if I suspected this account of laundering money, I could just right click and say, mark this as tainted. That just sets a property on that node, and you start seeing a couple things over there on the right. But I'll refresh it here, and we've got some color coding also built in. This pink one now has a value called tainted. This account has been tainted by us marking it as such, and that tag gets propagated whenever money has been sent or Ethereum has been sent to other accounts. So this account over here has also been tainted. And depending on what's in here, that continues on. So there aren't examples for this particular account continuing to send money, so or Ethereum. So let me pull up a different example that is a little bit longer. This is a set of transactions that have come through the blockchain, and if we mark this one here as tainted and refresh our nodes, then you can see their color coding here shows that they are marked as tainted. You can use these right-click, what we call quick queries, also set in the recipe to follow that directly without having to go through other parts of the graph. And if there are other transactions, we could keep following that along the way. But these are red because our tainted tag from this first node gets added to the second and increments a counter. So this node is 1 hop away from the original account. This node right here is 2 hops away from the original. So we can propagate that tag automatically using standing queries. And you've probably seen over here on the right, there's been some log lines out to the console because that's the action that we programmed it to do. Every time there's a new tainted account, go ahead and print a JSON object to the console telling us what's the ID of that node. Oh, there's another one. What's the ID of that node? What's this new tainted value? And just what action do we want to trigger? So we could set that to do other things as well. The last thing I'll show built into the application here is a REST API with Swagger documentation. So you can come in here and take a look and say, how do I define an ingest stream? Here's the schema. What data do I need to pass it? Where can I consume data from? So all of that is built into the application itself, as well as kind of a lightweight monitoring dashboard. So you can see some operational statistics about it running and doing its thing. So I encourage you to go play with it. It's free, open for everybody. Go play with it. If you do anything fun with it, we'd love to hear about it. Or if you make a recipe that you think anybody else might benefit from, please open a pull request and contribute it back to the repository so other people can do interesting things as well. And I will continue on from our demo here. And let's just ask this last question. Where does it fit in? So a streaming graph interpreter is meant to fit alongside other architectural components in your data pipeline. So basically anywhere that you have custom business logic, much of that can be encoded in standing queries handled through a streaming graph. And that custom business logic can start to get maybe cleaned up a little bit, or maybe it's easier to express some complex patterns in this way. And you can fold it into existing data pipelines in this gradual and incremental sort of way. And then really wherever it makes sense, alongside your other applications, in your data pipelines, wherever it makes sense to use this, can be dropped in and plugged into Kafka on one side and maybe stream out of Kafka on the other side. So we think of Quine really as sitting in between 2 Kafka streams. And so the Quine is really aimed at these two perspectives on the world, this event-driven data that allows us to focus on the data itself and not on the order of operations that we're doing with the data. So talk about the structure that you care about. Go ahead and consume from lots of sources and put them together into the same graph. It's schemaless and flexible, but still fast and can compute over it. And hopefully we can banish those limited time windows once and for all from our data pipelines. But the second side of that is really data-driven events. So setting standing queries and using the data structure to cause downstream events to occur. That happens automatically under the hood, propagated through the graph, and can accomplish complex event processing tasks with something as simple as just a database query. So you might use it, as we mentioned before, to update external systems, but you can also even call back into the graph and chain cipher queries together. Be careful. That can get very powerful very quickly, but both are options available and expressed in the same way. Quine as a streaming graph is really meant for this high volume data world. We have seen users in the community already taking what was typically months worth of work and accomplishing it in something like an afternoon. One of our users showed us recently pages and pages and pages of a SQL query that got replaced with one small Cypher query. He said it took him as much time to learn the system, implement it by himself, test it, get it all running, as it did for a whole team of engineers to go build the complicated SQL that still wasn't fast enough and still wasn't performant enough for their use case. Our mission is to turn high volume data into high value data. And you can find all sorts of details at quine.io and download Quine and go use it and contribute back if you find anything to help or other useful applications. But before we wrap, I want to offer one last insight. So we've been working on this for more than 7 years now and trying to use graph systems in streaming pipelines for a long time. The challenge is really just that they're not fast enough. We're very grateful to everybody who's done work in that area, lots of education in the industry, lots of insight about how to work with those systems and what they, how to express data in a graph and use that. But the real limitation is they've just been too slow to use in production or for any serious bits of work. And one of the main results of the research that we've been working on for the last many years is a new perspective that looks at that throughput problem or kind of the limitations of existing graph systems in a different way. And it's really this, that what we've come to realize from our work on this area is that graph's killer application is incremental computation. And this is what's been missing from the industry for a long time and what has kept a lot of graph applications limited to kind of toy-sized problems. But the incremental computation implemented in Scala, built on top of Akka, back-pressured by Akka streams, this sort of capability is really a game changer for finally using graph systems in high-volume, real-time systems in production. So with that, I am done.